Okay, so thank you everyone for attending. Welcome. This is the LVM tutorial for SecDev, and let me extend you a welcome to SecDev. My name is John Criswell. I'm an associate professor at the University of Rochester, and I'm assisted today by Ethan Johnson, one of my PhD students, and Colin Pronovost, my research programmer. All right, so so first let me go over a little bit of the of how we'll proceed here today. Since we do have a relatively small group, I think what I'll do is I'll allow questions via Zoom. If you want to, if you have questions on the material that I'm presenting, go ahead and use the Zoom raise hand feature. So there should be a little button somewhere on your Zoom client to raise a virtual hand, and I will stop and try to answer questions that I receive. If you have questions on the hands-on portion, such as, hey, I need, how do I download the virtual machine? How do I get it started? Et cetera, et cetera. We prefer that you ask those questions on Slack. Ethan and Colin will be answering those questions. Wave everybody, Ethan and Colin. And so if you could ask those questions there, or if you prefer to ask any other questions on Slack throughout the tutorial, that would be great. All right, so let's go over what our goals for the tutorial today is. There's two things we want to do. We want to create an LVM pass that instruments store instructions. So security practitioners oftentimes need to either record information about or control the behavior of instructions that write to memory. So if you're enforcing memory safety, for example, you need to control where store instructions are storing to memory. So we're going to create an LVM pass that modifies a program. So it modifies the program as it's being compiled to instrument store instructions. We're going to add a call instruction right in front of every store instruction so that we call some sort of function that does something with the pointer that is being used for the memory to reference. And then what we're going to do is we're going to optimize checks on the store instruction. So we're going to look at how we can make the instrumentation a little bit more efficient by alleviating checks on store instructions that are unnecessary. And so through this process, we're going to learn about the LVM intermediate representation, how to write an LVM pass, and all that other good stuff. All right, now what sort of background do you need for this tutorial, or at least to get the most out of this tutorial in its current form? This tutorial assumes that you have familiarity with C++ programming. Other language bindings exist for LVM, so you can write LVM passes in other languages. I believe you can write them in OCaml, Python, possibly even Rust. But C++ is sort of the native API for writing LVM extensions. LVM itself is written in C++, and so you have the greatest flexibility if you're writing your LVM extensions in C++. Now, what specifically do you need to know about C++? Well, you need to know how to use classes, pointers, and references. So that's going to be very helpful. You need to know how to use C++ iterators, and in particular, if you're familiar with using the standard template library, or STL as it's abbreviated, that's really going to help a lot. LVM tends not to use the STL. It uses its own container classes in place of STL containers, but they operate in much the same fashion, and they have very similar designs. So if you're familiar with iterating through a standard vector, or iterating through a standard list, or using a standard set, you're going to feel right at home using the LVM classes. All right, now we do have a hands-on component for this tutorial, and we have it built as a virtual machine, which you can download from the following URL. Ethan, is this URL posted in Slack? I believe you posted it a day or two ago, correct?
Yes, it is. Yes.
Okay. If you could just repost it so that it's like at the bottom of the Slack channel.
Yeah, certainly. If anyone needs assistance setting up the VM, downloading or setting up the VM, please ping me on Slack. I could definitely help with that. Okay,
thanks, Ethan. Yeah. So anyway, so you'll want to download this virtual machine image. It'll be a little bit before we actually get to any hands-on exercises. If you haven't downloaded the virtual machine and gotten it running already, probably a good time to start downloading it now. All right, and then when you start the virtual machine, the login username is user. So you want to log in as the user, very creative. The login password is LVM is cool, indicating that we have a small amount of bias among those of us that are presenting today. And the source code is in the directory /home/user/src/secdev19. So all of our source code examples as well as the LLVM compiler and all the other good stuff is located in that directory. Ethan, if you haven't posted that information in the Slack channel, if you could do that as well, I'd appreciate it. All right, so an outline of how we're going to proceed here is we're going to talk about the structure of the Clang LLVM C and C++ compiler. Then we'll review the structure of the LLVM intermediate representation, and then we're going to write an LLVM IR pass. And as part of writing an LLVM IR pass, we're going to discuss what the in-memory LLVM IR looks like, so what it looks like, what classes you use, and how to use those classes to examine and modify a program as it's being compiled. All right, so let's look at the structure of the LLVM compiler. And actually, before I move on, let me just pause for a moment. Does anyone have any questions? Raise your Zoom hand if you have any questions. Okay, no questions, so I'll go on. So let's talk about the the structure of the LLVM compiler. And the first thing that I want to note is that LLVM is a compiler infrastructure. It is a set of libraries for building compiler tools. So it's not just a compiler in and of itself. It is a set of libraries for building compiler tools. What kind of tools can you build? You can write tools that analyze software behavior, either by using static analysis or what we call dynamic analysis, where you add instructions into the program and then you run it. You can also write tools that control program behavior. So if you want to write tools that harden programs against attack, right? So you want to enforce control flow integrity or memory safety or code pointer integrity, or if you want to do fine-grained randomization, right? You can write tools that control program behavior. And as security practitioners, that's really what we're interested in with LLVM, is how can we use LLVM to analyze software behavior and then to control software behavior. Now, the LLVM compiler, at a high level, you can break it down into three parts: the front end, the optimizer, and the code generator. The front end is the component that takes the text of your program, the source code of your program, and parses it, right? Everyone remembers parsing from undergrad, right? Parses it and creates some sort of in-memory data structure representing the source code of the program. We call this in-memory data structure the Clang abstract syntax tree, or the Clang AST. Now, the Clang AST represents a program in its source code form. So it contains data structures that represents for loops, while loops, if statements, the ternary operator, if you're familiar with that and see the question mark colon thing. It even contains nodes in the abstract syntax tree for comments. So it actually records all the comments in the source code. And so what you get is an abstract syntax tree, which represents the source code of your program. Now, that abstract syntax tree is specific to the languages being compiled, and Clang compiles C-like languages. So C, C++, Objective-C, and Objective-C++, I believe, are the four languages that it parses. And so the abstract syntax tree is designed for those style of languages. And so it's not source level agnostic, right? So for compiler optimization and for other things like security hardening, like what we're going to do today, we transform the Clang abstract syntax tree at the end of parsing into another form called the LLVM intermediate representation. This is an architecture independent form of the code of the program that's in single static assignment or SSA form. And if you don't know what SSA form is, don't worry about it. I'll explain it later in the tutorial. So the LLVM IR is architecture independent. It's also source language independent. Which means that we can implement, optimizations and other transformations that are both hardware agnostic and also source language agnostic. So, for example, strength reduction, where you take, let's say I have an instruction that multiplies by 2. I may want to change that into a bit shift instruction, because bit shifting is typically cheaper on most architectures, right? Or if I want to inline functions, or if I want to do constant propagation, where I replace variables with a constant value. All this stuff is source language agnostic. It works on many different source languages, and it's also architecture agnostic. It's good for most architectures. And so the LLVM IR is what the optimizer uses to do what we call mid-level optimizations. These optimizations that are both source language and processor agnostic. Now, unfortunately, there are no processors that execute LLVM IR. You have to translate the LLVM IR to native code like x86, MIPS, ARM, Power, etc., in order to execute your program. And so there's a component called the code generator, which transforms the LLVM IR into another set of data structures, which we call the LLVM machine IR, the LLVM machine intermediate representation. This is a set of data structures that represents the actual machine code instructions that will eventually be emitted to a binary file and which will later be executed. So on x86, for example, you'll have, you may have one object which represents a move instruction and another one that represents an add instruction. So your instruction selection, your register allocation, your instruction scheduling, things like that happen within the code generator on LLVM machine IR. So as a developer, as someone that's writing a security hardening or security analysis tool with LLVM, the first thing you need to determine is which intermediate representation, the Clang abstract syntax tree, the LLVM IR, or the LLVM machine IR, you need to be using. If you need to know, for example, which exact registers a program is using, you need to write your transformation using the LLVM machine IR. If you want to analyze, where comments are in source code, you need to use the Clang abstract syntax tree. In this tutorial, we're going to be looking at the LLVM intermediate representation. The LLVM intermediate representation is kind of this nice in-between place. There's lots of security hardening and program analysis things that we can do in an architecture and source language independent manner with the LLVM IR. And a majority of tools written with LLVM IR work on the, so that work with LLVM work on the LLVM IR. So we won't be focusing on the Clang AST or the LLVM machine IR today. I mainly wanted to bring them up because you want to pick the right level of compiler in which to implement your analysis or your transformation. All right, let me pause for a moment. Any questions? Okay. All right, I shall proceed then. So the way that the optimizer is built, right? So here's our optimizer right here. The way that this is built, it's not built as one big piece of software, right? That would be a very, very complicated piece of software because there are tons of optimizations that modern compilers do. Instead, the optimizer is built as a set of passes. So it takes as input your program in LLVM IR form, and it sends it to one plugin called a pass, and that pass does one analysis or transformation on the program. It then outputs the transformed LLVM IR, and that is sent to a second pass, which does another transformation, another optimization of some sort, and then spits out another version of the modified LLVM IR. So basically, your program is basically fed, one pass at a time. Each pass implements one simple optimization. So maybe this first pass here, maybe this implements constant propagation, and then this pass here implements dead code elimination. And maybe you've got another pass out here that we write that does some sort of security hardening, right? So maybe it does memory safety hardening of some sort, right? So each pass does one thing. If I recall correctly from my compiler class, this is what we call separation of concerns. We don't write big passes that do tons of things. We write little passes that do very simple things. And then combined together, these passes collectively optimize and transform, and in our case, harden the program. So that's the structure of the LLVM compiler in a nutshell. Let's look at the LLVM intermediate representations, LLVM IR, that I keep talking about. LLVM IR is a language into which programs are translated for analysis and transformation. It is a language into which programs are translated for analysis and transformation. Now, LLVM IR comes in three different flavors. You have LLVM assembly language, which is a text form saved on persistent storage on disk, for example, for humans to read. Right? So LLVM assembly language is a text form readable by us mere human beings. The LLVM bitcode form is a binary form saved on storage, on persistent storage, for programs to read. So the way to think about this is LLVM assembly language is it's analogous to say assembly language for machine code, right? Assembly language is the human readable form. It has mnemonics. It has text that we can actually read that gets translated to machine code, which is the binary form that the computer actually executes. LLVM is very similar. We have the LLVM assembly language form, which humans can read, right? So it's a text form that we can read and we can actually modify if we choose to do so by hand. And then that gets assembled into LLVM bitcode form, which is a binary form saved on disk, which the LLVM tools use to load into memory and to write out to disk. The third form is the LLVM in-memory intermediate representation, the LLVM in-memory IR. This is a set of data structures used for analysis and optimization. So the way that your tools are typically built with LLVM is you will have your source code, say a .c file. That'll get translated into either an LLVM assembly file, a .ll file, or a bitcode file, a .bc file, like so. And then what we can do is we can actually load this into other LLVM tools, such as the optimizer. So right, then I'll draw a little optimizer here, right? And then the optimizer can read in either the assembly file or the bitcode file. I believe it actually handles both. And it parses these and it creates an in-memory data structure. So a set of data structures which represent the LLVM IR. So basically, it basically streams in the bitcode or the assembly language code. It transforms it, so it creates a data structure. It modifies this data structure to perform its transformations, and then it serializes this data structure back out to disk into another bitcode file, or if we want human readable form, an assembly file. Okay, so basically with LLVM, we have the in-memory representation, which is what our tools, the tools we're going to build, are going to modify. And then we have the persistent storage versions, which we can, either stream in when we're reading input bitcode, or we can stream out to save our program for later analysis and optimization, transformation. All right, so if you have your virtual machine ready, let's do a little example here. So if you go into your virtual machine, if you go into, I believe that source directory, you can type make. Make is going to compile the secdev pass. So we have a skeleton pass that we're going to show you how to modify later when we talk about how to write an LLVM pass. So make is going to compile that. Then after you run make, you can run sh compile tests. So you run make, you run sh compile tests. We have a number of little test programs, small C programs that do simple things that we're going to compile into the LLVM intermediate representation. So compile tests. That script does all of that for you. It takes all those little programs and compiles them into LLVM bitcode form. Now, if you cd into the run directory after doing so, you'll notice a whole bunch of BC files that end in .bc. Those are bitcode files. So those are LLVM IR forms of those source code programs that you just compiled by running the compile test script. And now what you can do is you can run the LLVM disassembler, LLVM-dis, that's the LLVM disassembler, and that'll disassemble a bitcode file and create the human readable form that us humans can actually understand. So it'll put its output into a file called global.ll. Okay, so if you have your virtual machine up and running, please go ahead and run these commands. If you have questions on them, please go ahead and ask on Slack or raise your hand in Zoom. And I'll give everyone a moment to do that. Just out of curiosity, how many people have the virtual machine downloaded already? If you have your virtual machine downloaded, please go ahead and raise your hand, your Zoom hand. Okay, so I see one Zoom hand. So I think we've only got one person that's actually downloaded this. So I think what I'll do, I assume everyone else is currently trying to download the virtual machine. I'll just go ahead and proceed. If we want to come back to this example later, we can. That'd be perfectly fine. But for now, I'll continue on since people are still downloading the virtual machine. All right, so if you were to look at this, the output of the disassembler. So if you were to look at the global.ll file, either by using more or less or your favorite text editor, what you would see is the following. You see that your bitcode file is basically a set of functions. So code is organized as a set of functions. So we have a function here, for example, set foo. So define basically says I'm defining either a global variable or a function. And so we have a function set foo. You'll notice that unlike C code, right? So it has functions like C, right? So that's somewhat C-like. But what isn't C-like are the instructions. So we have very, very simple instructions. We have a memory allocation instruction, alloca, which we'll discuss a little bit later. It allocates memory on the stack. And we have simple load and store instructions. So we have a load instruction here, which reads from memory, the store instruction that stores into memory, and a return instruction. So you'll notice that we don't have if statements or for statements. We don't have big complicated instructions. LLVMIR basically models something like a RISC instruction set. So we have very, very simple instructions in the LLVM intermediate representation. And so this kind of gives you a sense of what LLVMIR looks like. Now let's go over the structure of LLVMIR, because it has sort of a hierarchical structure to it. So every assembly file or bitcode file, right? Every bitcode file that you get in LLVM, we call it a module, right? A module represents, for those that know compiler speak, a translation unit, right? So a translation unit is a module. You can kind of think of a translation unit as a single C source file, right? So each bitcode file is a module, right? Now, what are modules made of? Modules are comprised of global variables, right? You got to have global variables, and then a set of functions. And that's all a module is, basically, a set of global variables and a set of functions. Well, what are functions made of? Well, functions are made of groups of instructions called basic blocks, right? So we have basic blocks. And then what are basic blocks made of? Basic blocks are made up of instructions. So basically, I take a whole bunch of instructions, I group them together into basic blocks. Basic blocks, by the way, are sets of instructions where control flow enters the first instruction, and then you execute all the way to the last instruction, the basic block, before doing some sort of branch. So we take instructions, group them into basic blocks. We take basic blocks, we group them into functions. We take a set of functions, sprinkle in some global variables, and voila, we have a module, right? We have a module or a bitcode file. And so here's a picture. Here's a picture of it for those of you that are like me, a little bit more graphically oriented. We have a module. So this whole thing here is a module. Our module has, a global variable. Since my slide isn't all that big, I've only got one global variable, but obviously programs can have many global variables. We have two functions, foo and bar, and each function, foo and bar, has three basic blocks, right? So each one of these is, and let me use a different color here. Each one of these is a basic block. So we've got 6 basic blocks, 3 in each function. And then as you can see, basic blocks are made up of individual instructions. So I've got, actually, let me draw that. So I've got some, add instructions. I've got some subtract instructions. I've got a little divide here to make sure that I can get a fault if I divide by 0. And I've got a return instruction, right? So we have instructions grouped into basic blocks grouped into functions. Functions with global variables comprise a module. Okay, any questions? Any questions? All right. Okay, so and again, I realize that not everyone has the virtual machines downloaded yet. So I'll just present what I have on the slide, and maybe we'll return to this later if people prefer to do so. We have a second example of LLVMIR. Again, you'll need to make sure that the pass is compiled. Sorry, let me get back to this color. Pass is compiled, make sure all the test programs are compiled. We go into this run directory, and we can disassemble the int_sum.bc file. So we have a bitcode file named int-sum.bc. All right, so this is what the source code looks like. So if you look at int_sum.c, which is in the test directory, right? So the test directory contains the source code, and then the run directory contains the generated bitcode files. This is a relatively simple program. So this is a little program. It just counts from 1 to 10, and it sums up all the numbers from 1 to 10, and then it prints them out, right? And then the function returns. And that's all this simple little program does. Now, over here on the right-hand side, I have some of the LLVM IR printed out. I couldn't fit all of it on the slide. But what you'll notice is that, again, we have these very simple instructions. We've got a load instruction here. We've got a comparison instruction here, and we've got a branch instruction here. We have a store here. We have an add. And let me see here, what else? And a call instruction. So calls function. So our call to, sorry, that's not our call to printf. Where's our call to printf? Our call to printf is right here. So this is our call to printf, right? So there's a printf call right there. This add right here, is this operation right here. So you can start seeing how this loop is translated into LLVM IR. So we have these instructions. In LLVM IR, at least in the assembly version, basic blocks are basically denoted by this little label here. So you'll have a label and it ends with a little colon. That shows the beginning of a basic block. And the basic blocks end with some sort of terminator instruction, either branch instruction or return instruction. We'll talk about terminator instructions later. And so we can group the basic blocks as so. We have one basic block here, which is basically the condition for the loop. It basically determines should we execute another iteration of the loop. We've got another basic block here. The body of our loop, so where we're actually doing that addition, is this basic block here, the basic block name for.body. We've got another basic block here. And then finally, this is the basic block that is at the end of the loop. So when the loop exits, we jump to this basic block and we call printf. Okay, so this has 1, 2, 3, 4, 5. This example has 5 basic blocks. There are 5 basic blocks that make up this loop. I should say, or actually I should more accurately, there are 4 that make up the loop, and then 1 basic block makes up the printf code that occurs after the loop. Okay, any questions on where the basic blocks are in this program, or at least in this little code snippet? Okay. All right, now the LLVM instruction set. So we've talked about the structure. We have instructions, we combine them together into basic blocks. Basic blocks comprise functions, and then functions comprise with global variables comprise a module. Well, what sort of instructions do we have in LLVM IR? Well, the LLVM IR, as I mentioned previously, is a RISC-like instruction set. So we have virtual registers in SSA form. Again, you don't have to worry about what SSA form means if you're not familiar with it, but we have virtual registers. All right, so we have virtual registers, unlike a real machine. So real machines have a limited number of registers, right? So x86, I think, has 16 registers or something. PowerPC 32 has, I think, 32 integer registers and 32 floating point registers. Real machines have a limited number of registers. In LLVM IR, we have an unlimited, an infinite number of virtual registers. We can have as many virtual registers as we want. When the program's translated to native code, these virtual registers will either be assigned to a real register or they'll be assigned to memory locations. But in the LLVM IR, we don't worry about where they are actually placed when the program is compiled to native code. We just know that they're virtual registers and we can have as many of them as we want. Now, LLVM, being RISC-like, it has load instructions which read data from memory objects into virtual registers. We also have store instructions which take value in virtual registers and store them into memory objects. So they write them into memory objects. And then we have some instructions that allocate memory objects like alloca, which I showed previously, and I'll talk about a little bit more later. And then all of our other instructions read or write virtual registers. So all of our other instructions read or write virtual registers. So it's very RISC-like. So add instructions, for example, the add instruction does not read or write memory. It accesses virtual registers. So its inputs are virtual registers and its output is virtual registers. Same for subtract, multiply, divide, bit shift, et cetera, et cetera, et cetera. So all of our instructions read or write virtual registers, except our load instructions and our store instructions. And so again, kind of taking an example from our sum program. So again, we have this program here. It has a loop where it's adding the numbers 1 through 10. So the first 10 positive integers. And here's the LLVM IR code for that. And what you'll see here, as I mentioned previously, is we have a load instruction. So we load from memory. So these are pointers. So I here is a pointer to the variable I, or to the memory location that contains I. Sum is a pointer that points to a memory location that contains the variable sum. Right. So these are stored in memory. So I and sum are stored in memory. So we load them, and then we add the values in the virtual registers together and store it in another virtual register called add. And then we take the value and add, and we store it back into the memory location pointed to by sum. So here are our load instructions. Here's our add instruction. And you'll notice that, again, what we do is we load values from memory into virtual registers. And then the add instruction or the subtract instruction or multiply, divide, whatever it is that we want to do, whatever computation we want to do, we operate on the virtual registers and we store our result into a virtual register. Right? So we have loads and stores like a RISC architecture, and then all of our other instructions operate on virtual registers. Yes, and then we do a store. All right. Now, what sort of instructions do we have for quote unquote computation? Well, we have, the usual suspects. We have the arithmetic and binary operators. So we have 2's complement arithmetic, add, subtract, multiply, divide, all of that good stuff. We also have bit shifting and bit masking operations. So we have bitwise, and inclusive or, exclusive or. We have an instruction for inverting the bits. We also have instructions for bit shifting, so being able to do arithmetic shift left, logical shift right, things like that. Not mentioned on the slide, we also have floating point instructions. So we have floating point add, floating point subtract, etc., etc. Now in LLVM-IR, at least the LLVM-IR that we're currently using, pointers are actually typed. And so we have a special instruction that does pointer arithmetic. So for example, if you have, say, a pointer to the beginning of a structure and you need a pointer that points into a field within that structure, that is an example of pointer arithmetic. Or if I have a pointer to the beginning of an array and I need to calculate a pointer to the 5th element of the array, again, that's pointer arithmetic. LLVM has a special instruction for that, which we really won't be covering today, but it's called get element pointer, or GEP for short. So we have typed pointer arithmetic. I want to note that LLVM is always changing. So LLVM is being actively developed as we speak. And so as a result, one of the things that the community is doing is they're slowly phasing away from these typed pointers. So I don't know what's going to happen with get element pointer, but it may be going away at some point. But for right now, we have typed pointer arithmetic. And so we don't use the arithmetic to complement binary instructions for pointer arithmetic. We use the special get element pointer instruction. We then also have comparison instructions. We have integer compare and floating point compare, among others. And what these comparison instructions do is they compare two values. So you say, I want to compare two integer values, and I want to do signed less than or equal, or I want to do unsigned greater than or equal. And it compares the two values based on the criteria that you specify, and returns a Boolean result indicating true or false. So true, the comparison is true. Value X is, first input's less than or equal to the second input, or it's false. The first input is greater than or equal to the second input. Now our memory accessing instructions. So these instructions, all of these instructions here work on virtual registers, right? So as I mentioned before, it's a very RISC-like instruction set. So our arithmetic and binary operators, our point arithmetic, comparison instructions, these all work on virtual registers. Now, to get data into and out of virtual registers, we use memory access instructions. And there's 4 types of memory access instructions that I want to mention today. There's a load instruction, which reads data from memory and loads it into a virtual register. There's a store instruction, which takes a value in a virtual register and writes it to memory. Then there's also the atomic operation. So LLVM provides atomic operations for those people that like writing parallel programs. So we have atomic compare and exchange, which basically reads a value from memory, does a comparison, and if the comparison succeeds, writes a new value into the memory location. And then there are atomic read, modify, write instructions, instructions like fetch and increment, for example, that exist within the LLVM-IR. So we have these 4 groups of instructions. I mentioned the atomic instructions because people oftentimes forget them. So they're, for example, if you want to instrument all instructions that write to memory, you have to get more than just the store instruction. You also have to get the atomic compare and exchange and the atomic redirect modify write instructions, because those instructions also write values into memory. So these are our memory accessing instructions. Let me pause here for a moment. Do we have any questions? Feel free to raise your Zoom hand if you have any questions. Okay. All right. All right. So reading and writing memory is great. Adding, subtracting is just fine. But what about control flow, right? So if I have like an if statement, or if I have a loop, how do I express that in LVMIR? Well, remember that instructions are grouped into basic blocks, and basic blocks are a set of instructions where control flow jumps to the beginning of a basic block. So it starts executing the first instruction and executes all the instructions through to the end. That last instruction is an instruction type of instruction that we call a terminator instruction. The terminator instruction is at the end of every basic block. So every basic block ends with a terminator instruction. And that terminator instruction indicates which basic block or basic blocks to jump to next, right? So every basic block ends with one of these terminator instructions. The most common type of terminator instruction is a branch instruction, and LVM, unsurprisingly, has two types of branch instructions. It has the conditional branch and the unconditional branch. So an unconditional branch is a branch that always jumps to another basic block. So there's only one other basic block that it jumps to, and it's explicit, right? So here, for example, I have this basic block. Let me draw an arrow. I have this basic block here. You'll notice that this branch instruction jumps to this basic block here. So this branch instruction is an unconditional because it always branches this add instruction here, right? Which that add instruction is the beginning of a basic block. Branches, by the way, can only jump to the first instruction of a basic block. You can't jump into the middle of a basic block. Okay, if we take a look at, say, this branch here, this branch is a conditional branch. So this branch takes as input a Boolean value. And if that Boolean value is true, it jumps to one basic block. And if that Boolean value is false, it jumps to another basic block, right? So an unconditional branch, there's only one basic block it ever jumps to. A conditional branch, it either jumps to one basic block or another based upon some condition. So if the condition is true, we jump to this basic block. If it's false, we jump to that basic block. Now, there are other sorts of terminator instructions. I won't be going over it in detail, but there's the switch instruction. The switch instruction is basically a conditional branch on steroids. It basically has a set, it takes an input value and then a set of pairs of basic blocks and values. And basically, if the input value matches one of the output values, you jump to the basic block corresponding to that output value. So if I have, say, if I had a situation where I have 5 different basic blocks that this basic block here can jump to, what I would use is a switch statement, which is kind of a generalized form of the conditional branch. So we have several different terminator instructions. I won't go over all of them today, but conditional branch and unconditional branch are two of the most common. The other one that's very common is the return instruction. So the return instruction is also a terminator. So if I have a return instruction, what it says is, okay, this function is done executing, return to the function that called this function. So if all these basic blocks are in function foo and bar calls function foo, then the return instruction calls execution return to the call instruction that called foo within bar. All right, so if I've got bar over here or over here, and bar has a call instruction to foo, and let's say this is the function foo here, then this return here is going to return control flow back to right after that call instruction in bar. Now, call instructions, something that's perhaps not intuitive, but call instructions are not terminator instructions. Call instructions can occur anywhere within a basic block, so long as they're not the last instruction in the basic block. And that's because when a call instruction calls a function, the expectation is that function will eventually return, and control flow will proceed through the rest of the basic block after the call instruction. So call instructions can occur in the middle of a basic block. All of your other quote unquote branching instructions occur at the end of basic block. So unconditional branches, conditional branches, switch instructions, which by the way are not like the C switch statement. They're similar, but they're not the same. The switch is basically a generalized conditional branch. these instructions are terminators. They terminate basic blocks. So they are always the last instruction within a basic block. And so going back to our int sum example, if we were to look at those basic blocks that that we looked at before, we see that we have a number of conditional and unconditional branches. So for example, here at the beginning of the loop, you'll notice that we have this comparison instruction, I compare. So we're doing an integer comparison, assigned less than or equal. That's what SLE stands for, signed less than or equal. And we're comparing whatever's in 2, which is loaded from the variable I. We're comparing it against 10, right? So we do this comparison, and then we do a branch. So the branch takes the comparison as an input. If the comparison yields true, we jump to the basic block that's labeled for body. So we jump to this basic block here. If the condition is false, we jump to the basic block labeled with for.con.cleanup. So for.con.cleanup, this basic block here. So we either jump to here if the condition is true, or here if the condition is false. Okay, so this is our conditional branch, and we've got one of these here. We also have 3 unconditional branches, right? So if we look at this basic block here, this one here, and this one here, you'll notice that they end with a branch instruction. The branch instruction only has one basic block to which it jumps. So this is an unconditional branch. So when for.con.cleanup, when it executes all of its instructions, when it's done, it'll jump to for.end. It'll jump here. That's where it jumps to. For.body, when it's done, it'll jump to for.inc. For.inc is right here. So these are unconditional branches. They have no conditions. They'll always jump to these locations. And then finally, we have return instruction, right? So this last basic block here corresponds to this code right here, lines 10 through 12. And basically we have return instructions. So we returning the value 0 to the caller. So equivalent to return 0 here. So this is also terminator instruction. So this basic block terminates by returning to the function's caller. Okay, any questions? Any questions? Shravan, let me unmute you. Yep. Go ahead.
Can you hear me? Testing.
Yep.
Yep. I was just curious that you took a few seconds to actually call out that call instructions are not terminators. I was just curious as to whether there's actually any advantage in making them terminators, both with respect to analysis or the way we think about compilers in general. It's a bit of an open question. I was just curious to get your thought on that.
I've never actually considered that. I know the reason why they're not terminators, right? They're not terminators because control flow jumps to the called function and then it eventually comes back, right? So basically, if you kind of think of like the dynamic execution of the program, the called function is sort of dynamically inlined when you do a call instruction, right? So I think that's logically why it's not a terminator instruction. I don't think there would be an advantage to making a terminator instruction. The reason why we have terminator instructions is because they make the control flow graph in a program explicit. So one thing that I didn't mention is that if you'll notice, these are labels, right? These labels here are the names of basic blocks, and what you'll see is that you don't have a dynamically computed basic block address in LLVM-IR, right? Or at least in traditional LLVM-IR. There's a little exception. I'll mention that in just a moment. But these are not. You can never. Your branch instructions are not indirect. They're always direct branches, and so the control flow graph is explicit. And if the control flow graph is explicit, then it's much easier for compiler analyses to transform the program, right? Because they don't have to reconstruct the control flow graph. In some compilers or in some tools, especially binary writing tools, you have to reconstruct the control flow graph. So you just see a whole blob of instructions. And you have to figure out where the basic blocks begin and end. With LLVM-IR, the compiler just makes it explicit. It says, I have this basic block and it branches to these 2 other basic blocks, and that's it. And you know exactly which 2 basic blocks they jump to. Now, there is an exception to this. a few years ago, and maybe even more than a few years ago now, they added an indirect branch instruction to LLVM IR. This was mainly designed to support interpreters, I think like the Python interpreter. It's not used by most C programs. So indirect branch is something that you almost never see. And my suggestion is if you're writing compiler transformations, don't use it because it can create, it can create control flow integrity issues and that sort of thing. So indirect branch is best avoided. So the original LLVM IR was a little bit more quote unquote pure. It didn't support such things. In order to implement certain interpreters efficiently, and I forget exactly what kind of interpreters they are, they added this indirect branch. I'm ignoring that because like for regular C programs, you don't need indirect branch. You can have a completely explicit control flow graph. Does that answer your question? Let me see. May have to unmute him. Shravan, does that answer your question?
Oh, yes. Yeah, I think so. I think there's definitely it's an interesting subject. And I think some of, yeah, I think broadly, yes. Broadly, yes. I am curious to see exactly all of the implications if we were to make it a terminate instruction, because I can imagine that analysis via traces could be something that this could help with, but yeah, definitely a fascinating insight.
When you say traces, you're saying like a dynamic analysis?
Potentially, because one of the things that comes to mind is that LLVM does have an interpreter.
Mm-hmm. And
when you're running LLVM IR via this interpreter, we do have access to live traces.
When you say like live traces, traces of what? Of actual?
Of execution.
Of execution? Okay.
Yeah.
Possibly. We can chat about that offline or after the tutorial or something. It's not clear to me that would actually be valuable.
Fair enough.
So,
anyway, okay. But yeah, thank you for your detailed answer.
Welcome. Brian, go ahead. Oh, sorry, I need to unmute you. Sorry, let me, they've given me too much power today. Brian, go ahead.
I had a comment about Shravan's question. I was thinking, if you think about the first basic block, the entry basic block of the called function, I think what happens is if you made the calls function a terminator, then you would just save yourself the quote unquote space of having the first basic block appear, as an appendix, as a suffix, if you will, adjoined to the basic block that's doing the calling. So if there are three callers, then the first basic block of that called function appears sort of linked to each of those call sites. And if you separated them, you would just have that basic block appearing once in the graph with 3 unconditional jumps to it.
To be honest, that doesn't make any sense to me because the basic block of the called function is in the called function is in the called function. It's not in the call instruction. Right. So the call instruction takes the name of a function. That function is comprised of basic blocks. The first basic block is the entry basic block.
Right. And in the current paradigm, isn't that entry basic block? It just starts immediately after the call instruction, yeah?
No. The entry basic block is within the function. It's within the called function.
Gotcha. Okay. Gotcha. But they don't get inlined that way. Okay, thank you.
No. They don't get inlined.
That's great. Okay, thank you.
So I mean, if you inline the function, so the way that static inlining works, right? The way that static inlining works is you take the call instruction, you find the callee, you take out the call instruction, and you take all of the callee's code and copy it into the caller.
Sure.
Right.
Okay, awesome. Thank you.
Okay, welcome. Other questions? And let me go and lower all the hands. Let's see, where's the button for that? I can't find the button for it. All right. Okay, Brian lowered his hand. So thank you, Brian. Okay. I used to know where that button was, but now I can't find it. Anyway. All right. Any other questions? All right. So, so we now have our instructions for computation, adding, subtracting, multiplying, dividing, and all that other good stuff. We have branch instructions. Now we can have if statements and loops and all of that good stuff. Now the last thing we need is we need to actually allocate memory, right? Because again, we have a RISC-like instruction set. We have to read from memory and store to memory in order to do things. So first we have the allocate instruction, which I mentioned earlier. The allocate instruction allocates stack memory. So you basically say alloca, you give it the amount of memory that you want to allocate, or I think in current LLVM, you give it, say, like a type, and the compiler figures out how much space it needs for that type and allocates it, and it returns a pointer in an SSA virtual register. So alloca returns a pointer to the memory allocated on the stack in an SSA virtual register. Now, what about heap memory? Well, for heap memory, what we do is we insert call instructions to heap allocation functions, such as malloc. So heap allocation is done just by calling a function that returns a pointer to the memory that it allocated. So we don't have any special heap allocation instructions. Rather, we just call functions for a particular language. In the case of C, it's malloc, that allocate memory and return a pointer to it. And again, the return value is in an SSA virtual register. So return values of functions are passed in SSA virtual registers. That's how we allocate heap memory. And what about global variables? Well, global variables are declarations, right? So they are not part of functions. They are just declarations that are at the top level of a module. They're not really instructions, right? So, you know, they don't, quote unquote, get executed, right? But they do allocate memory, right? So they basically reserve space so that when the program is finally compiled down to native code and you load it, there is space reserved for that global variable. Now, global variables in LLVMIR are different from global variables in C, and this tends to cause a bit of confusion. So in LLVMIR, global variables allocate global space. So there's a region of your address space that's used to hold global variables. It reserves some space in that region. But the global variable itself is an SSA virtual register that points to the global memory, right? So in C, for example, if I do, if I have a C file, right, and I write, say, int foo at global scope, foo is the name of the integer, right? It's the name of the integer, which happens to be stored in global memory. In LLVMIR, if I have a global variable foo, which I forget the exact syntax, but I think it's like global %foo. And then somewhere here, I think it's the type. So maybe it's global int foo, global int %foo. Foo is not an integer. Foo is an SSA virtual register, which points to an integer. So foo is a pointer to this globally allocated integer. Right. And so that's a key difference with global variables in LLVMIR versus global variables in C. In C, global variables can be any type that you want. And when you use the name of the variable, you're talking about the memory that's actually allocated in that region of memory reserved for global variables. In LLVMIR, this global keyword allocates an integer's worth of memory in the global memory region. And then it creates a pointer foo, which points to it. So foo is a pointer. It is a pointer which points into memory. And so in order to access this memory, I have to either load from foo or store to foo like I would use any other pointer. All right, so pointers in LLVMIR point to memory, and then you use load and store instructions to read and write that memory. Okay, any questions on memory, especially global variables? I know that global variables are a little different compared to C, which is what most people are used to. So any questions before I proceed? Okay. All right, now let's talk about single static assignment form, or SSA form. So in single static assignment form, each function, as I mentioned before, has an infinite set of virtual registers, right? So each function has an infinite set of virtual registers, as many as it wants to have, right? Now, why do we have to have an infinite number of virtual registers? It's because only one instruction can assign a value to a virtual register. So single static assignment, as my dad always says, it's just as the name implies. There can only be one instruction within the function that assigns a value into that virtual register. There's only one instruction that writes a value into that virtual register. That one instruction is called the definition of the register. It's called the definition, right? So let's look at this little add instruction that I have on the slide. So I have an add instruction. It takes virtual register X, virtual register Y, adds their values together and puts the result in virtual register Z. If I have this instruction within a function, this is the only instruction that can write to Z. I cannot have any other instruction that writes to Z. So I cannot write, for example, I cannot write, Z equals sub of say %X and %Y. So this is not allowed, right? That would violate single static assignment. There would be more than one static instruction writing or defining the value in that virtual register. So there's only going to be one. It's kind of like Highlander, right? There can be only one, at least one in each function, right? Now, an implication of this. So the reason why we use single assignment form is that for certain program analyses, single static assignment form allows us to use more efficient algorithms. And I'm not going to be getting into SSA-based algorithms today, but I just want to point out that that's the reason why LLVM uses it, is that you can use more efficient analysis algorithms. But there's an interesting implication which is going to affect, how we use in-memory LLVM-IR. And that is the fact that because the instruction set is in single static assignment form, because every virtual register is only defined once in each function, the instruction and the register it defines are synonymous, right? So a question that I oftentimes get, later on, like in the in-memory, when we start talking about the in-memory IR, is, well, okay, I have this variable Z, right? I have this virtual register Z. I want to know what instruction writes to it. I want to find the instruction that writes to virtual register Z. And I have to explain, well, you don't have to find it because these two are synonymous, right? These two are synonymous. So this and this are actually the same thing. They're one object. To try to show this visually, I've drawn up this, right? So if I have, again, I add X and Y together and I get Z. In the in-memory LLVM-IR, so when we actually take the IR in the bitcode and we bring it, we deserialize it from storage and we create the in-memory data structures, we're going to create one object, happens to be called a binary operator. The operator is going to be add, its operands are X and Y, and its name is Z. So this object represents both the add instruction and virtual register Z, because there's only one instruction that can write to Z. So in the LLVM-IR, the instruction that writes to Z and the virtual register Z itself are one and the same. They're the same object. They're the same thing. That may be a little bit confusing now. What I'll do is, if it's still confusing once we start talking about LLVM-IR, when we start talking about the in-memory LLVM-IR, we can stop and revisit. But the thing I want to point out is that because we have single static assignment form for virtual registers, the instruction that defines the value in a virtual register and the virtual register itself are the same thing. They are synonymous. They are one and the same. All right. Okay. Before we jump into writing an LLVM pass, let me pause again. Any questions from anyone before we proceed? Okay, just out of curiosity, raise your hand if you've got your virtual machine up and running. Just like to do a quick check on that, see how, if progress has been made. Okay. Rodithia, if you could please lower your hand. Let me ask another question. How many people, and I hate to put people on the spot, but raise your hand if you're actually following along with the tutorial. You're trying to download the virtual machine and do the hands-on exercises as we go. I'm just curious, how many people are actually wanting to do that, and versus how many people are just kind of hanging out and kind of seeing what's going on here. So if you're downloading the virtual machine or trying to set it up, please raise your virtual hand. Okay. All right. Thank you. That's good to know. All right. So let's move on to writing an LLVM pass, All right. So as I mentioned before, the way that the LLVM Optimizer is built. So, and it's the optimizer, and we're going to change it into sort of a security hardening tool as well, is it takes LLVM-IR, it's divided into a set of passes. Each passes takes the in-memory LLVM-IR, analyzes it or makes modifications to it, and then passes it along to the next pass. Right, so it's kind of like hot potato. Your program is an LLVM-IR form. That LLVM-IR form of your program is the hot potato. It's given to each pass. Each pass transforms the potato, transforms the program, and then hands it off to the next pass, right? And so at the end, you get a final LLVM-IR, which represents the program that's going to be translated to native code. Now, there's two types of passes. The first type of pass is an analysis pass. And an analysis pass does not modify the program, right? Analysis pass does not modify the program. What it does is it analyzes the program. So it performs some sort of analysis and provides information about that analysis out of band to other passes, provides it out of band to other passes. So an analysis pass, for example, might count the number of add instructions within a function, or it might determine which pointers point to which allocated memory objects. We call that points to analysis. So it might do that. Or it might, for example, do some sort of security analysis and report on, how many dangerous functions were called. So are you calling like sprintf in this function? And if so, how many times? So it might do an analysis like that. So it makes no modification to the program. It makes no modification at all, but it calculates some feature of the program, and then it can provide that information to other passes if they desire. The other type of pass is the transformation pass, or in the LLVM documentation known as an optimization pass. An optimization pass or transformation pass, as I sometimes call it, because not all optimizations optimize code. Sometimes we're trying to harden the program against attack, or we're trying to instrument it in order to do profiling. A transformation pass modifies the program. So it inserts instructions, or it removes instructions, or changes the order of instructions, but it modifies the program in some way. Now, sometimes the transformation pass needs some sort of analysis information. So it might need to know, okay, which basic blocks dominate which other basic block. So a dominator block is a basic block that must be executed before other basic blocks are executed. So it may call an analysis pass to say, hey, I need this information. Please go calculate it for me and return the results. Right? So transformation pass modifies a program, and it may optionally, at its discretion, call other analysis passes, methods in the analysis passes to get information out of band about the function or the program or the basic block that it is modifying. Now, so in terms of source code, analysis passes and transformation passes look exactly the same, right? The only difference is that an analysis pass will not modify the program at all. A transformation pass may optionally modify the program. Now, there's for each for both analysis passes and transformation passes. Again, transformation passes are called optimization passes in the LLVM literature. You have different types of passes. You have the module pass, you have the function pass, and the basic block pass, right? And I'll discuss briefly when to use each different type of pass. But you have module pass, function pass, and basic block pass. And basically, you have different passes that you use in different types of passes that you use in different circumstances. When you write a pass, you will derive from one of these classes. So if you write a module pass, you'll derive from the module pass class. If you write a function pass, you'll write code that derives from the function pass class. And if you write a basic block pass, you'll write code that derives from the basic block pass class. Now, there are other types of passes called loop passes, region passes, etc. I call these the funny passes. I recommend ignoring them. If you're starting out with LLVM-IR, it can be very difficult to determine when you should use a loop pass, when you should use a region pass. You can never go wrong using a module pass, function pass, or basic block pass. And so my recommendation is to, at least when you're beginning with LLVM-IR, when you're first beginning work with LLVM, stick to module pass, function pass, or basic block pass. Ignore all those other fancy pass types. Ignore the loop pass and the region pass. Now, there are rules for different types of LLVM passes. So a pass can only modify values and instructions at the scope of a pass. So a module pass can modify anything in an LLVM module. So you get past a reference to a module, it can modify anything in that module that it wants. So it can add and remove global variables, add new functions, remove functions, change instructions within functions, move basic blocks around. It can change whatever it wants. A function pass is a bit more restricted. A function pass should not modify anything outside of the function. So a function pass is given a function, and it's basically said, hey, either analyze or transform this function. A function pass should not be peeking at anything outside of that function, and it should definitely not be modifying anything outside of that function. So function passes should not modify anything outside of the function. And then, as you can guess, a basic block pass should not modify anything outside of a basic block. So basic block pass is given a basic block to transform, and the basic block pass should not modify anything outside of that basic block. Now, my suggestion, especially when you're starting out with LLVM, is when in doubt, write a module pass. You can never go wrong writing a module pass. It may not be the most efficient thing to do, but it will always work correctly. So when in doubt, write a module pass. All right, so let's write a simple pass. So a pass is comprised of two source files, a .h file, which basically defines the pass, and then a .cpp file, a C++ source file, which provides the code that implements the pass. We're going to write a simple pass called the secdev pass. And so in our .h file here, we're going to find a new structure called struct secdev. This is going to be our pass, and it's going to inherit from module pass. So we're going to write a module pass because it's always safe to write a module pass. Can't go wrong writing a module pass. Right, so we're going to write a module pass. And then there's some boilerplate stuff. There's some stuff that pretty much every pass has. So in the public methods and public members, we're going to have a static char ID value. This is a pass identifier variable. You don't have to do anything with it yourself. You just have to make sure that it exists because it's used by the LLVM compiler to assign an identifier value to your pass. So the code in LLVM that actually runs passes one at a time needs to have that static identifier value for your pass. Your pass is going to have a constructor. It's going to have a constructor, and that constructor is going to pass the ID value into the module pass method. Right, and then otherwise the constructor doesn't do anything. Right, so it's an empty constructor. Passes should have names. So there are features in LLVM where a tool can print out the names of all the passes that it's going to run. So we have a get pass name. Actually, let me clear this bit. So we have a get pass name method. And it just simply returns a string. This gets casted through the magic of C++ casting and operator overloading to a string ref, which is a special LLVM type to efficiently implement strings. So our pass is called the LLVM tutorial pass. And then most importantly, we have to have an entry point for our pass. So our pass is going to have a method called run on module, right? Run on module. It's going to take a reference to a module, and it's going to return a Boolean value, which we'll talk about momentarily. Okay, so this is all stuff that like every module pass has. Like you'll find this in every module pass that you ever see. Now, your module pass can also have private methods, right? We're not, if we write code that's going to transform a program, we're not going to write all the code in the run on module method, right? So we may have helper methods, that are private to our class, that are private to our module pass, that it will use to help it along. And so in our case here, we have a visit load inst. Sorry, let me underline that a little bit better. A visit load inst method and a visit store inst method, which take a reference to a load instruction and a store instruction, respectively, right? So these are private methods. The LLVM compiler is not aware of them. Our run on module method will use them to do its work. Okay, any questions so far? Any questions? Okie dokie. All right, so our run on module method, as I mentioned, is the entry point for our module pass. So when LLVM decides that it's time to run your pass, your run on module method is going to be executed, and it will be passed a reference to a module as input. So a reference it's kind of like a pointer in C++, except that it's kind of like a pointer, but you're passing a value by reference. So you get the module and you access it like it's a variable, but in fact it's a pointer to the module that you can mutate. So you're going to receive a reference to this module. And then using this module, you can locate functions, basic blocks, and global variables from the module, right? So because it's a module pass, it can modify anything. The module class itself, so the module object that is passed to your run-on module method, has pointers, if you will, pointers or iterators to everything else that is contained within it. So if I have a module, reference to a module, I can look at all the functions in the module, all the basic blocks in the functions, all the global variables in the module, etc. Now, what about that Boolean return value? What are you supposed to return? Well, what you do is the return value is true if the pass modifies the program, and it's false if it leaves the program unchanged. So an analysis pass always returns false. An analysis pass never, ever modifies the program, right? So it always returns false. The run on module method of an analysis pass always returns false. A transformation pass, or again, as the LLVM documentation calls it, an optimization pass, can return either true or false. It will return true if it did modify or might have modified the module, or it'll return false if it knows that it made no changes at all. If you're always in doubt for a transformation pass, you can always conservatively return true. You can say, I don't know if I modified anything, but I'll just say that I did and return true. So true is always conservatively correct. However, some LLVM can sometimes do things more efficiently if it knows that your pass didn't make any changes. So if you have, say, a transformation pass, let's say we're instrumenting store instructions, and you go over the program and you find no store instructions, you can return false, because you can say, hey, I looked for store instructions, I didn't find anything, so I didn't change anything, right? In some cases, LLVM can avoid running subsequent analysis passes because you haven't changed your program. All right. All right, so let's look at the simplest run on module method in history. All right, so in our C++ source code file, first thing we have to do is we have to register our pass. So we have to tell the rest of the LLVM compiler that our pass exists and what its name is. So that's what this line does here. So we call register pass. Register pass is essentially a class that is that's templated. We give it the name of our pass secdev. We declare a global variable. It doesn't matter what the name of that global variable is. We oftentimes call it P or pass or some name that we don't really care about, but it just has to have a name because C++ says so. And then the first argument is basically a short name that we can use on the command line to run our pass. So in our tutorial, if I remember correctly, and Ethan and Colin can correct me if I'm wrong, but we're using the opt tool to run our passes. So opt, basically you use a -load option to load your pass into opt. And then once you do so, you can use -secdev, SECDEV, we can use /secdev to tell it to run our pass. So we say, okay, the short name of our pass is secdev. So if you want to run our, give the name of our pass on the command line is secdev. And then a description of the pass. It's the LLVM tutorial pass. Okay, so that just registers our pass. And again, that's pretty much boilerplate. You're going to see that line of code in virtually every module pass implementation you ever see. And then we have our run on module method. So we have secdev : run on module, returns a Boolean, gets a reference to a module object, right? So we have a module object, so a C++ object of type module class, and returns true. So this module, although this module doesn't modify anything, it just pretends that it does and says, yeah, I modified the module. Okay, and that's the simplest pass that you can possibly write. Simplest module pass you can possibly write in LLVM. All right, now let's actually make this pass do something, right? This is great. We've written our module pass, but if we stopped here, you probably think you got cheated in the tutorial. So let's go on and actually make this pass do something. But in order to make this pass do something, we need to understand the in-memory LLVM IR. We need to understand the set of data structures that are going to be constructed that represent that bitcode file, right? So we have a set of data structures that represents our program that's being compiled. We need to understand the structure of those data structures so that we can make reasonable changes to those data structures to transform our program, right? Now, remember that I talked about, the structure of an LLVM bitcode file, right? You have a module, modules have global variables and functions have basic blocks have instructions, right? Well, surprise, surprise, LLVM has a class for each type of IR object, right? So there is a module, right? So there's a module class. We have functions. So there's a function class. We have basic blocks. So we have basic block class, and then we have instructions. So there's an instruction class, all right? So for all those things we talked about, modules, global variables, functions, basic block instructions, we have a class for each one of those. LLVM has a class for each one of those. Moreover, each class provides iterators to iterate over the objects within them, right? So remember how we said, okay, modules are comprised of global variables and functions. Functions are comprised of basic blocks are made up of instructions. Well, each class provides iterators for the objects within it. So for example, if I give you an LLVM module, there is iterators that iterate over all the global variables within that module. Likewise, there are iterators that will iterate over all the functions contained within the module, right? So modules are made up of functions. So the module class has an iterator that will allow you to iterate over all the functions in that module. And then surprise, surprise, functions, the function class has iterators that will iterate over all the basic blocks that make up the function, right? So if I give you a reference or a pointer to a function, there is an iterate, you can use a method on that function to get an iterator to all the basic blocks that are in that function. And then similarly, the basic block class has an iterator that iterates over all the instructions that comprise the basic block, right? So if I give you a reference to a basic block, you can use a method to get an iterator that will iterate over all the instructions contained within that basic block, right? So in this example here, I've got 3 basic blocks. So I can iterate over all the instructions in each basic block, each function. I can use a method to get an iterator to this list of basic blocks, and the module, I can get an iterator to iterate over all the functions within that module, right? So this is where iterators come into play, right? Because if I give you a module, you can use a module to iterate over all the functions. You can use an iterator from the function to iterate over all the basic blocks in that function. And then for each basic block, you can iterate over all the instructions within that basic block. So each class provides iterators for items it contains. So the module : iterator iterates over all the functions within a module. The function iterator, function : iterator, iterates over all basic blocks within the function. And then the basic block iterator iterates over all the instructions within the basic block. So let's say, for example, that I want to add code to, I want to write code where I want to iterate over all the instructions within basic block. So let's just assume for now, let's just assume that I have a pointer to a basic block, right? So I've got a basic block pointer BB, right? So BB is a variable that points to a basic block object, right? So it points to a basic block object within the program that's being compiled. I want to iterate over all the instructions within that basic block. What I can do is I can create basic block iterator IT and IE. IT is going to be our iterator. IE is going to represent the end of the iteration list. And I can say for IT equals basic block begin. So the begin method returns an iterator to the first, an iterator that points to the first instruction in the basic block. I'm going to set IE to BB in. So this is basically a terminating iterator. So it points to, the last element in the list. And then while IT isn't equal to IE, I'm going to increment IT. So an iterator is this variable where each time you increment it, points to the next element within the container. The container here being a basic block. And then what I can do is I can, using this address dereference craziness here, I can cast that to an instruction, right? So I can take that iterator variable and basically get a pointer to the instruction to which the iterator refers, right? So this code iterates over all the instructions in a basic block. So within this loop, the variable I points to the current instruction that we're iterating over within the basic block. Okay, let me pause and ask if there's any questions. Are there any questions on this example? Okay. All right, so let's say that we have our secdev.cpp example. So we're writing our pass and we want to iterate over all the instructions within a module. All right, so we have a module, we want to iterate over all the instructions within the module. Here is what we would do. Move this over here. Here's what we would do. we have our module here, right? So we have a reference to the module. So what we're going to do is we're going to iterate over all the functions in the module. So fi is going to be our function iterator. So fi equals m.begin. So m is our module. Begin gives us the iterator to the functions. So fi equals m.begin. Well, fi is unequal to m.end. So while we have other functions left to iterate through, we're going to increment fi. So fi now is an iterator to functions, right? So if I do the proper casting, I can get a function pointer, right? A pointer to a function object, more accurately. Okay, so now I've got functions. Now I want to iterate through all the basic blocks within this function. So I do function iterator bi. Bi can iterate through basic blocks. I do function iterator begin. So basically this arrow takes the function iterator and changes it into a pointer to a function object. So fi begin, so bi equals fi begin. Bi is unequal to fi end plus bi. So now bi is an iterator through the basic block. So bi is going to iterate through all the basic blocks within that function. Okay, so we have that. Now we have a basic block, right? Now we have to iterate through all the instructions within the basic block. So, okay, so basic block iterator it equals bi begin, right? So we're going to start, we're going to iterate through all the instructions within the basic block. So instruction iterator starts with bi begin, goes until bi end, and then we increment it, the instruction iterator. And then finally, inside this nested loop, I can take the instruction iterator, I can dereference it and take the address of it, and that gives me a pointer to the instruction. So again, in C++, when you have an iterator, you have to like dereference it in order to get the thing that it's pointing to. And so that's how we get the instruction, the pointer to the instruction object here. Brian, you have a question. Let me go ahead and unmute you.
Yeah, I noticed a syntax difference. So the the elements of the members of M are getting access with the dot, and the other guys are getting arrowed. So yep. One of those is you get the object directly, and the other one you're getting a reference to them. Or can you say a little bit more about that?
Yes. So if you'll notice here, we're past a reference to M, right? So M is a reference. These others are essentially, well, these are iterators, and so since the arrow notation basically dereferences the iterator, right? So this arrow here is essentially doing the same thing as this thing here, that little asterisk. So that arrow is dereferencing the iterator, right? And so then what I'm getting instead is I'm getting an iterator, and then I'm dereferencing the iterator, which is very similar to dereferencing a pointer value. I'm not really big on C++ syntax. I basically know it well enough to get it to do what I need it to do. I find C++ type rules, especially when it comes to iterators, a little bit confusing. So I apologize for that. But yes, you have observed correctly that this is a reference, right? So that's a reference, C++ reference. So you treat it like a variable. That's why you have the little dot there, right? These iterators you treat like pointers. For whatever reason, in C++, you treat them like pointers, and that's why you use the arrow. Does that answer your question, Brian?
Yes, it does.
Okay. Any other questions? Any other questions? Okay. So what we have now at this point, right? What we have now in this point is we have code that can look over every instruction in the program, right? So we can, so we've written code that's going to basically loop through every instruction in the program, right? So if we added code into this loop, we could do something with these instructions that we're iterating over, right? So we've basically got code that's going to iterate over all the instructions in a module, right? But now we want to do something. We want to do something with those instructions. And this leads us to the LLVM class hierarchy. So anything that is an SSA value in LLVM IR is a subclass of the value class, right? So we're in C++, we have subclassing, right? So anything that is an SSA value is a subclass of value, right? So anything that's an SSA value, so a global variable, which remember again is a pointer to globally allocated memory, the value of an instruction, a function. So functions are actually SSA values. The name of a function is a pointer to that function in LLVM IR. So all these SSA values, all of them are subclasses of value. So if I have, say, an instruction generates an SSA value. So as a result, it is a subclass of value. Furthermore, all instruction classes are a subclass of instruction. So anything that can be in SSA form is a subclass of value. So instruction is a subclass of value. All of our different instruction types, so alloca instructions, which allocate stack memory, call instructions, which call functions, add instructions, which add values together. These are all subclasses of instruction of class instruction. So we have an instruction class, which is a subclass of value, and then all instruction classes are subclasses of instruction, right? Now, similar instructions will share a common superclass. And so all the instruction types in LLVM are basically kind of grouped together in nice, nice convenient classes. And so to show you say sort of a subset of the LLVM class hierarchy. This is a simplified LLVM class hierarchy. The real class hierarchy is larger and far more complicated. But you have values, so everything is a value, or nearly everything is a value. Instructions are values. Global values are also values, right? Now I can have different types of instructions. I have the load instruction, which represents a load instruction. So load inst is the class that represents a load instruction. So a load instruction in the in-memory IR is going to be an object, a C++ object of load inst class type. I have a store instruction. So a store instruction is going to be represented by a C++ object of type store inst class. And then I also have the alloca instruction, which represents an alloca instruction, the instruction that allocates stack memory, right? And all of these are subclasses of instruction, right? So they inherit from the instruction class. So load inst inherits from instruction class, store inst inherits from instruction class, alloca inst inherits from instruction class. Likewise, LLVM has a number of different global values. Functions are actually global values. So are global variables. So global variables, which we've talked about previously, are a subclass of global value. So they inherit from global value. So there's a few ramifications of this. One is that if there's something that you want to do with a particular object, let's say you want to iterate through all of its inputs, all of its operands, if you will, or you want to learn, like okay, if I have a load instruction, what is the SSA value that's used as the pointer from which I'm supposed to load? All of those methods either come from the class itself or it comes from one of its superclasses, right? So for example, if I want to know, well, I want to iterate through all the uses of this load inst, right? There are methods to do that you can use on a load instruction, on a load inst, but they're not defined here. They're defined here. They're defined in value because everything here is a value. So one of the things that I want to point out is that if you're looking for documentation on a particular class, let's say you have a load, a pointer to a load inst, and you're like, okay, there's got to be a method that does something on this load instruction. You may want to check the documentation not only for the load instruction, but also the instruction class and the value class, because it's possible that those methods that you think should exist for the load instruction also exist for other instructions. So therefore, they'll be defined in the superclass, not in load instruction itself, right? So the first thing to note is that you want to understand this inheritance tree, right? You want to know which classes inherit from which other classes, because when you're looking for a method that does something, that method may not be defined in the immediate class that you're looking at. It may be defined in one of its superclasses, right? So maybe there's a method I want to use on load inst, but it's not documented in load inst because it's actually a method that comes from value or instruction. The second thing is that if you notice in our little code example, right, so to clear this out here, if you notice in our little code example, when we iterate through all of the instructions, we get a pointer to instruction class, right? But we're going to want to know, okay, I have a pointer to an instruction. So I have a pointer to an instruction of class. I have a pointer to an object of class instruction, right? So I've got a pointer to an instruction. I want to know if it's a load instruction or if it's store instruction or an alloc instruction. I want to know what kind of instruction it is, which means I need to figure out what subclass the object actually is, right? So I get a pointer to an object. It's of the superclass type. I need to figure out what subclass type it actually is, right? And so LLVM is going to give us the ability to do that. So a common problem that you get in passes is you get a pointer to an instruction and you say, okay, is this a load instruction or a store instruction or an alloc instruction, or is it something else? You need some way of being able to tell that. one of the things about C++ is that you can have a, if I have something of say like loadInst class, I can use an instruction pointer, and a pointer of type instruction to point to it, because load instructions are also instructions. So, we have this problem in our pass. I've got a pointer I to an instruction. I want to figure out if it's pointing to a load inst or a store inst or an allocate inst or something else. And so how do I do that? Well, LLVM provides very nice helper functions to help us with this. And so the two casting functions that we're going to talk about today is ISA and DynCast. So ISA is a templated function. So it's the function ISA, that's ISA. It takes as its template input a class and returns true or false if a value is of that class. So let's say I have a pointer to instruction. And it's I, right? So I have I is a pointer to instruction. And I want to know if it's a branch instruction. So what I can do is I can type ISA branch inst I. And this function will return true if I points to an object that is a branch, and return false if I does not point to an object that is a branch. All right, so ISA is ISA. Is this instruction a branch instruction? Is this instruction a load instruction? Is this instruction a store instruction? All right, so that's how I can tell if I is a branch instruction or not. Now, ISA returns a Boolean value, right? And sometimes what we want is we actually want a pointer of the subclass type. So maybe, for example, I want to create a new pointer BI, which is of type branch inst, which points to the actual object. So here we have a similar function, similar to ISA, but the return value is a little different. It's called DynCast. It's short for dynamic cast. It returns a pointer to the object of that type, of type class, if the object is of that type, or returns null otherwise. So let's go back to our instruction pointer I. So if I is an instruction pointer and I use DynCast branch inst, if I is pointing to a branch inst, then I get back a pointer that points to a branch inst object. So I can do branch inst pointer bi equals DynCast branch inst I. So bi, if I is a branch, so if I is a branch, bi will be set to a pointer of type branch inst. And then if I is not a branch instruction, then bi is just set to null. And so in this way, I can easily determine whether something is a branch instruction or not. And then if it is a branch instruction, I've got a pointer to the branch instruction, and I can call the branch instruction methods on that object. So let's see this in action, right? So let's go back to our code that is iterating through all of the basic block, that's iterating through all the instructions in the basic block, right? So I've got my variable BB, which points to a basic block. I iterate through all the instructions in the basic block, right? So that's the code that we saw before. So we've got our iterators, IT equals BB begin, end equals BB end, while IT is unequal to end, iterate to the next instruction, right? And so we get an instruction pointer here. Now let's say that we want to know if this is a store instruction. Is this a store instruction? And if it's a store instruction, I want to pass it to a method that takes as its input a store instruction. All right. So what I do is I use DynCast. So I take I and I say, okay, dynamically cast it if you can to a store instruction. So if it's a store instruction, dynamically cast it to a store instruction. And we're going to put that result in the variable SI. Let me draw that a little bit better. So we're going to put it into SI. All right. Now, if SI is unequal to null, so in other words, this cast succeeded, right? So if SI is unequal to null, that means it's pointing to a store instruction. And now I've got a pointer to it that is of type store inst, of store instruction. So now I can pass it to a method that takes a store instruction as input, right? So if I'm iterating through instructions, right? If I'm iterating through instructions, I can use DynCast to test whether that instruction is of a particular subclass. And if it is of a particular subclass, I can get a pointer to it of that subclass type. Okay. Any questions? Any questions on this example? All right. All right, so let's take what we've learned now and actually add a runtime check. All right, so we have this visit store inst method, right? So basically what we've done is in our, and let me scroll back here. So, you know, in our run on module method, right? In our run on module method, right? We've written our code that iterates through all the instructions in a module, right? We've also added code that can take this instruction, test whether it's a store instruction, and if so, can pass it to our visit store inst method, right? So we have that private store inst method. To remind you, scroll back here. We have this private method here that takes as input a store instruction. All right, so now, okay, let's fill in this visit store inst method, right, to actually do something with that store instruction. All right, so let's add a runtime check. All right, so here's the code of our visit store inst method. We've basically written it for you here. There's a few things that we're going to do here, right? So if I have a store inst, store instruction, right? What I want to do is I want to insert a call instruction right before that store instruction. That call instruction is going to pass the pointer used in the store to some function. That function is going to do some sort of check. Maybe it does a memory safety check. Maybe it does some sort of validity check. Maybe it does some sort of debugging purpose, right? But our goal here is that every time we see a store instruction in the program, we're going to insert a call instruction right before it. That call instruction is going to take as its input the pointer that's used in the store instruction. All right. Okay, so the first thing we need to do is we need to get the value that's used as the pointer in the store instruction. Now, if we look at the LLVM documentation, we'll talk about where to find that documentation at the end of the tutorial. The store inst class has a method that returns a value pointer to the pointer value that's used in the store instruction, right? So we have SI here. SI is a pointer to a store instruction. We call the get pointer operand method on it. That returns a value pointer, right? A value pointer which points to an object that represents the pointer value that's actually passed, that's actually used by the store instruction, right? So we store this in a variable called pointer. So pointer points to an object. We know that it's a value. We don't know anything more than that, and right now we don't actually care. We don't care if it's a pointer to a global variable, if it's a return value from a call to malloc. We don't care if it's the result of an alloc instruction, right? All we care about is that it's a value, right? So it's a value, and we're going to retrieve it using the get pointer operand method. Okay. All right. So now we have the SSA value, right? We've got the object upon which we want to pass to the call instruction. The next thing we need to do is we need to cast it, right? So LLVM allows casting between types. That's how it supports, nasty C programs that can have, cast operations in them. And so we need to add a bit cast instruction. A bit cast instruction will take this pointer operand, and this pointer operand can be of any type, right? So this pointer value used in the store instruction, it could be a pointer to a structure, a pointer to an integer, a pointer to an array, a pointer to an array of structures, etc. Right? We don't know what type it is, so we're just going to cast it to a pointer to a character, right? So the void pointer type in LLVM IR is basically a pointer to an 8-byte value. That's what LLVM uses for its void pointer type. So what we're going to do is we're going to get the LLVM context. So LLVM has this idea of context. Each module is created in a context, and everything within the module belongs to the same context. So the store instruction shares the same context as the module. So we're just going to grab that context there. And then, sorry, let me make that a little bit more clear. And then what we're going to do is we're going to create a bitcast instruction. So our bitcast instruction is going to take as its first operand the pointer, so the value that's going to be used in the store instruction. And we are going to cast it to the void pointer type. And so this method here, or function here, just gets the void pointer type for us. We're going to give it the same name as the original pointer value, and LLVM will basically create unique names for all SSA virtual registers. So basically what we're doing is we're creating a new instruction. This new instruction needs a name. We're going to base that name off of the pointer's name. So LLVM will take that name. If it's not unique, I'll add some characters on it to make it unique. And then this last field here says, okay, here's the instruction before which you should create this new bitcast instruction. So in our LLVM we have a store instruction. We want to create that bitcast instruction right before that store instruction. So this last parameter here says, here's the instruction before which you should insert the bitcast instructions. We're going to create a bitcast instruction, and when we create it, it's going to be created right before that store instruction, right before it. O-R-E, store. Okay. So now we've got our bitcast instruction. Now the next thing we need to do is create the actual call instruction. So we're going to call a function. This function is called check memory. And we've got in our past, we've already created a global variable that points to it. So we're going to call check memory. So we're going to call inst create. So the call inst class has a static method which will create new call instructions. We'll create new call instructions. And so to create the new call instruction, we call the static method of call inst. We pass it the function we want to call, the SSA value for the function we want to call. That's in the variable check memory. We're going to create an array of the parameters that we want to pass. There's only one parameter we want to pass, and that's the pointer. And so we pass that here. Notice that this is the result of our bitcast instruction. So our bitcast our pointer variable now points to the bitcast instruction. Right, so a pointer variable now points to this thing, right? So we make that the parameter of our function. Since our check doesn't return since it has a void return type, we give it an empty name. And then again, we insert it before the store instruction. So we're going to create a call instruction. Yes, we're going to create a call instruction. We're going to put it right before the store instruction. So we're going to create it here. And it's going to call check memory. Is going to pass the result of this bitcast. So if this is the result of bitcast, we're going to pass that here. Okay. And so with these four lines of code, I can insert a call instruction, which takes as its input the parameter that's going to be used in the store instruction. I can pass it to some sort of function. I can implement that function in, say, a runtime library, right? And I can link that into my program. And so whenever we're about to store into a memory location, we can call this function. This function can perform some sort of check on that memory location. Okay, any questions? Any questions? Okay. All right, so if you got your virtual machine up and running, and you want to try some of this out, what you can do is you can cd into the run directory. You can run, say, the global program or the intsum program, and what you'll see is there's a function called check memory. So we made our own implementation of the check memory function. The secdev pass is going to insert a call to the check memory function before every store instruction. And our implementation of check memory, it's not really going to check memory. What it's going to do is just going to point out the pointer value that was passed to it. So when you run the program, right? So when you compile the programs using our secdev pass, and you run them, what you'll see is you'll see not only the output of the program, but you also see the output of the check memory function. The check memory function is going to print out every pointer that is used by a store instruction in the program. So every time this program writes to memory, you will see the memory address to which it is writing. So you can see exactly where in the virtual address space the store instructions are writing to. Okay. Excuse me. Any questions? Any questions? All right. Now, can we optimize away some of these unnecessary checks, right? So maybe I don't want to print out the address of everything that's stored to memory. Maybe I only want to print things out when I don't really know what they point to, right? So maybe I don't want to print out pointers to global variables, and maybe I don't want to print out pointers to stack allocated memory, right? Because I know that those values are safe. I know that those values are correct. So maybe I don't need checks on those, right? So for example, like let's assume, for example, you're doing memory safety enforcement, right? If you're doing memory safety enforcement, right? If I've got a pointer that points to a global variable, right? I don't need to do a runtime check because global variables are always allocated. They're always safe, right? So I can eliminate calls to check memory on pointers that point to global variables. Excuse me. Likewise, I can eliminate pointers that are the result of an alloc instruction. So if I do a stack allocation and then I immediately use the pointer that points to that stack allocated memory in some sort of instruction, in some sort of store instruction, I don't need to check it because I know it was just allocated, right? I know it's been allocated. I know it hasn't been freed. Stack allocated memory is freed when the function returns. I forgot to mention that earlier. So I don't need checks on pointers to global variables. I don't need checks on pointers that are the result of an alloca, right? Because I know that those are safe, right? So, how can I enhance my pass to optimize those away, right? So let's say I've got this example here. So again, I've got visit store instruction. This is the exact same code as before. But what we want to do here now is if some condition holds true, I just want to return, right? So basically, if the pointer points to a global variable or to stack allocated memory, forgo adding a runtime check. You just let it go, right? So just to return here, don't insert all of this code that actually inserts the bitcast instruction and the call instruction. Okay. So what code do you think we might put in here? So let me turn it over to the audience now. Based on what we've seen, what code would you put in here? What code would you put in here? All right, so let's back up a bit. So in our code here, right, I have a pointer to some value, right? So I've got an object of some type, right? I've got an object of some type, right? I know it's of class value, right? I know it's of class value, right? So I know it's of class value, but it might, it's probably a subclass, right? It's the object's actual type, right? Its actual dynamic type. It's probably something else, right? It could be a binary operator. It could be a binary operator. It could be a get element pointer inst, so GEP inst, right? It could be a load inst. It could also be, say, an alloc instruction, so an alloca inst. Or maybe it's a global variable, right? Which is the global variable. If I can spell it right, global variable class, right? So I have this pointer here, right? So I have a pointer, it's of type value. It points to some sort of object, right? This object is for sure a value, so it's an SSA value of some sort. But it could be an alloc instruction, a global variable, a binary operator, a GEP instruction, a load instruction. Which of these types of objects does it need to be in order to do the optimization, do you think? So say out of these 1, 2, 3, 4, 5, out of these 5 different types of objects that this value could be, which ones would allow me to forego adding a runtime check? Okay, so let me back up and ask it another way. So do I need to check on a global variable? So for example, do I need to check on a global variable? Anyone? All right. Well, it turns out that no, we would not need to check on a global variable, right? Global variables are globally allocated. They never get freed, right? So if we have a pointer to a global variable, right, if we have a pointer to a global variable, it does not need to be freed. So what I want to check for is pointer a global variable, right? So is pointer, is pointer, here, let me clear this off now. So is this value here, is it of subclass global variable? Right? Is it a subclass global variable? All right. So what I'd want to do is I want to ask, if, that pointer is a global variable, all right? If pointer is a global variable, right, I can return, right? I don't need to add a check on it, right? Likewise, if it's an alloc instruction, I don't need a check either, right? So looking at the class hierarchy, right, what I want to see is okay, I've got this value. My pointer is a value of some sort. It could be a load instruction. It could be a global value, could be an alloc instruction. It could be a global variable. I want to do the optimization if it's one of those two objects, right? So if my store instruction is storing into stack allocated memory, right? So if it's storing in stack allocated memory, so it's an alloc instruction, the result of an alloc instruction, or if it's storing into a global variable. So the pointer operand to the store instruction is a global variable, then I want no runtime check. And so then what we can do is this, right? So we just want to know if this pointer is a global variable or if it's an alloc instruction. So we write if is a global variable pointer or is an alloc inst pointer, return. So what this means is that if I have, say, an alloc instruction, which returns a pointer, right? So its result is a pointer, and then I do a store using that pointer, I don't add a call to check memory, right? I don't add a call to check memory at all, right? Likewise, if I have a global variable and I do a store into that global variable, right? Again, I don't need to call check memory. I know that that pointer is good for some definition of good. In this case, that's validly allocated memory, right? It's not pointing in the middle. It's not pointing to the return address on the stack. It's not pointing into unmapped memory, or anything like that, right? So basically, if it's a global variable or if it's an alloc instruction, I can forego adding the call to check memory, right? And that would make my checks a lot more efficient. So let me go back real quick. All right, any questions? Any questions before we move on? Okay. Oh, sorry, Brian, let me unmute you. Go ahead.
I was looking back a couple slides, and you had the, where was it? Shoot. You had, when you were checking the, what kind of instruction it was, you did the bind inst cast instead of the ISA on the, when you were checking the store instructions, I guess a few slides.
Yes, yes.
What was the advantage there?
The advantage is that I actually get a pointer of type storeInst, which means that now on that object I can call the methods that belong to storeInst, right? Let's see here. So for example, so basically what the issue is that since LLVM is written in C++ and it's got this class hierarchy, I can have a pointer to an object, right? And that object, its class may be, for example, storeInst. So store, let me capitalize that correctly. So its class is storeInst, right? But because its type is storeInst, it's also an instruction.
Mm-hmm.
And then because it's an instruction, it's also a value, right? Because all store instructions are instructions, all instructions are values,
sure,
right? And so what happens is with the, if I have, say, a basic block, right? A basic block is made up of instructions, right? So, if I can go back, say, to this, not that diagram, this diagram here, right? Basic blocks are made up of instructions, but these instructions can be of different types, right? So add and subtract are binary operator instructions. Branch is a terminator instruction. Alloca is an alloca inst. Load is a load inst. Store is a store inst, etc. Right? So these individual instructions can have different C++ types depending upon what they are, right? And so when you iterate through a basic block, you get, all these, whatever these are, whether the load insts or store insts or terminator insts or binary operators, whatever they are, they're all subclasses of instruction, right? So what you get is you get an instruction pointer. So you know that this object, is either, it's an instruction or some subclass thereof, right? But if I've got a pointer to instruction, like, so let's say I've got, let me draw something here.
Sorry, if you, in the check on so I guess it's slide 44.
Yep.
If you did, why wouldn't you just say if I is a store inst?
Oh, so I think what you're talking about is, let me pull up the example here. This example here, right?
Yes.
Right. Because if I did isa only returns Boolean, right?
So you'd still have to do the cast, in other words, to get.
Yes, you'd still have to do the
Sure.
cast. So dynamic cast or dynecast does the isa and the cast all in one go, so it's more efficient.
So even if I really is a store instruction, you still have to cast it in order
Yep.
to, because the iterator returned it as a instance, as a just plain instruction.
Exactly. Exactly.
Thank you.
Yeah, and that's because of C++. So, and object-oriented programming, I think, in general. So yeah, that's exactly it. Good. Other questions? Any question at all? Okay. Well, so moving beyond the tutorial, right? So hopefully this tutorial, I hope what we've been able to achieve is to give you sort of a brief, gentle introduction to LLVM, so that you have an understanding of how LLVM is structured, how passes are structured, and how you can actually start writing your own pass. So hopefully today we've given you like the first steps, on a journey to being able to write compiler transformations. So one might naturally ask, well, where do I go beyond the tutorial, right? One thing that some of you may be interested in is data flow analysis, right? So for example, if you're interested in data flow analysis, well, what are the algorithms for trying to understand program behavior? There's a number of places that you can look. So for books, there's the Dragon book, which has a dragon on the front cover. It's called Compilers, Principles, Techniques, and Tools. If you're more mathematically oriented, there's a book called Principles of Program Analysis, which I think is developed by people who do slightly more formal methods like stuff. But if you're interested in more mathematical introductions to data flow analysis, I would check that book out. So both of these books are going to give you a nice introduction to data flow analysis. Then you might also consult papers. So there are papers on SSA-based algorithms. There's research papers on that. And then if you're really interested, there's the original Kim Ullman paper on iterative data flow analysis. So the data flow analysis that we typically start teaching in compiler classes, that's covered in the Dragon book. So it's covered in this book here and covered in 2 of the chapters in Principles of Program Analysis. That was originally developed by Kim and Ullman. And they have a very nice paper that explains the framework for that iterative data flow analysis. Now, what about helpful documents for LLVM? So I've given you just like a small taste of LLVM. Where can you find more information? The good news is that LLVM is quite well documented. So there's lots of resources that you can find online that are available for you right on the LLVM website, https://llvm.org. There's the LLVM language reference manual. So if you want to know all the instructions that LLVM has to offer, in the LLVM IR, the LLVM language reference manual will give you all that information. There's the LLVM programmer's manual. This basically contains a small amount of documentation on the most important classes, methods, and functions that you need in order to write LLVM passes. So for example, ISA and dynecast are documented in the LLVM programmer's manual. You'll also want to know how to write LLVM passes. And today we've only talked about module passes, and we've only talked about transformation passes. So if you want to read up on how to do analysis passes, function passes, basic block passes, and when to use them, there's a special document specifically on how to write an LLVM pass, and it's entitled, appropriately enough, How to Write an LLVM Pass. And then finally, as you've probably seen, LLVM has this class hierarchy. So every object in the in-memory intermediate representation is of some type and it has numerous superclass types, right? So it's a subtype of a whole bunch of other class types. And so how can you get information on, the class hierarchy, and how can you figure out which methods each class offers? Well, LLVM routinely generates Doxygen documentation for its internal code. And so if you go online to the LLVM webpage, you can find the Doxygen pages. And the Doxygen pages are these nice set of pages that are all hyperlinked together, which give you information on all the LLVM classes and their superclasses and their subclasses and the methods that they provide to programmers. So if you're saying, okay, I have a load instruction, there must be some method on a load instruction that tells me, what its pointer parameter is. What is the name of that method, and what inputs does it take and what outputs does it take, right? All of that is in the Doxygen document for the load inst class. So each class is going to have a page that lists all of its methods and their inputs and comments on the methods that explain how to use them, and superclasses, so that if the load inst doesn't have a method that you're looking for, maybe one of its parent classes does. And so you can, link through the documentation looking for the documentation for that superclass. So the Doxygen documentation, I use it all the time. When I'm writing LLVM passes, I use it all the time to figure out what the methods are named, what they do, etc. Now, you may also be wondering, well, how do I get involved with LLVM? Especially if you're an undergraduate or graduate student. How do I get involved with LLVM? You might look for research on program analysis. So the National Science Foundation has a research experience for undergraduates program. And some of that money is used by various researchers around the United States to fund research for undergraduates to do research work on program analysis. And not all program analysis work, but a lot of program analysis work uses LLVM. And so that's a good way to, if you're an undergraduate and you're looking for a way to start with LLVM to get your feet wet with it. LLVM also participates in Google Summer of Code. So so each summer, we have a number of mentors from the LLVM community. Some of them are professors, some of them are developers in industry. All of them work with LLVM and they mentor projects proposed by students. And so if you are a student and you are looking to get paid by Google to do some work on an open source project, you can go and ask on the LLVM developers mailing list what open projects there are and look for open projects or suggest an open project and get feedback on it. And then submit a proposal, to Google Summer of Code. And that happens every summer. I think proposal time is, don't quote me on this, but I want to say it's around April or so. So it's kind of mid to late spring that starts getting off the ground. Something new that Tanya Latner is spearheading is something called Outreachy. So Outreachy is an organization that develops projects for underrepresented students. And so LLVM is starting to do some work with that. We've recruited one mentor so far, and I think in future years we'll be recruiting more mentors for that. And so so that may be a project and an organization that may be of interest to people. Many companies use LLVM, Apple, Samsung, Google, Facebook, Cray, among others. They build a lot of tools with LLVM, and so they may offer jobs for internships that have you working with LLVM tools. If you're looking for those sorts of job opportunities, they're oftentimes posted on the LLVM developers mailing list. If you're looking for LLVM related jobs or LLVM related internships, that's a good place to look. And then finally, there's the LLVM developers meeting, which has been held virtually thanks to COVID-19. Thanks, COVID-19. That was sarcasm, by the way. And usually in person when we're not suffering from a global pandemic. There's typically 2 each year. One is held in California and one is in Europe. And it's got fun for the whole LLVM family. So there's talks, there's posters, there's bird of a feather sessions, etc. I think they've actually also added a PhD research competition. So now you can, PhD students can go and submit posters on their work and short little presentations on their work and compete, I think, for some sort of prize. And so the LLVM developers meeting, again, there's one in Europe, one in California every year. Finally, something I want to point out is that LLVM has a community. LLVM is a community. And so you don't have to go it alone. If you want to start working learning how to write LVM passes, learning how to do program analysis and transformation. Maybe you want to build stack analyses that look for security bugs in programs. Maybe you want to write tools that harden programs against attack. Maybe you want to build debugging tools. If you're just getting started out, you don't have to go it alone. We have a community there to support you. And in particular, I want to point out the LLVM developers mailing list. When we made the LLVM developers mailing list, just to kind of tell you a little story, I didn't think that was the best name. And it turns out that I was, at least in my opinion, I was right about that, because some people feel that the LLVM developers mailing list is only for people who are working on the core LLVM compiler. This is not true. This is one of those misconceptions that we've kind of been fighting against ever since. The LLVM developers mailing list is a place to ask questions and get answers for anyone that is using or developing with LLVM. So if you're building a new tool with LLVM, if you are starting a new project with LLVM, if you have a question on how to use the LLVM internal API, if you have questions on ISA or Dimecast or the class hierarchy, if there's something that you just can't figure out from the documentation, please ask on the LLVM developers mailing list. There are people there that are willing to help you. It's not just for core LLVM developers. I will remind people that it is a volunteer thing. So people that answer questions are volunteer. So I can't guarantee that you will get an answer to a particular question or that you'll get an answer in any particular length of time. It is an open source project. It is community driven, and it's community led and basically performed by the community. So just keep that in mind. But if you ask a question, you are likely to get an answer. We want people working with LLVM. We want to introduce, new people to LLVM. So, don't feel like your question is too ignorant or too stupid for a mailing list. If you've got a legitimate question at LLVM, please ask. We want to know. All right. Finally, we'd love to hear your feedback. So we've got a Google form set up at the following URL. Ethan or Colin, if you could paste the link in the slides into Slack so that people can get it via Slack, I'd appreciate it. But we'd really like to have your feedback. We want to know what's working for you in this tutorial, what's not working, what could be better. We also want to know a little bit about who's attending these tutorials and what they want to get out of them, so that we can better construct the tutorial to match the needs of the SecDev community. So any feedback you can give us, we would greatly appreciate it. That concludes our tutorial. Or at least the planned presentation. I think what we can do now, since we have about, 45 minutes left, is I think Ethan, Colin, and I can just hang out. We can answer questions. If people want to play around with the hands-on component and ask us questions about that, we're happy to do that as well. With that, I thank you for your time, and we'll take questions. Let's see here. Brian, go ahead.
Are there, I would call it like libraries of, sort of commonly used passes, or, is there a pretty extensive set of templates you might look to?
So the pass that we have, the template we have in our virtual machine that's basically the template for a module pass. So you're free to use that. I think there's also example code in the LLVM source base itself. So as far as templates and whatnot, there's plenty of examples there. LLVM, by the way, I just kind of assumed everyone knew this, but I realized I should have stated it explicitly. It's open source. It's under an open source license, so you can actually see the code. You can modify the code. And of course, since it's open source, as long as you follow the license, you can take an existing pass, gut it out, and replace your own stuff with it if you find that easiest. In terms of your other question, are there existing passes to use so that you don't have to build everything from scratch? Absolutely, positively, yes. Whether the ones that you want specifically are there, I don't know. But for example, there are passes that do dominator analysis, right? So if you need to know, okay, which basic block, which basic blocks must be executed before these other basic blocks execute, we call that a dominator tree. There's passes for that. There are very simple alias analysis passes. If you look outside of the LVM source base itself, I think there's a group, I want to say it's from University of Utah, that has developed actually, I think there's two groups that have developed strong points to analysis algorithms for LVM. So I think a group from University of Utah basically took the data structure analysis originally written by Chris Latner, dusted it off, and made it into something that's workable and usable. So that's data structure analysis, or DSA. And then I think another group built something points to analysis called SVF, which I think is much more heavyweight. So I think it's slower, but probably more precise. That's available as well. And then there's all sorts of optimization passes. So there's a document somewhere on the LVM webpage that lists like all the analysis and transformation passes that come in the core compiler. So you can look through that list, and then if if what you need isn't there, then you can ask on the developers mailing list and see if anyone has already written an analysis pass that does what you need.
Thank you.
Yep. Forgive me, I'm terrible at names, but Kryakos. Please go ahead.
Yes, that's okay. That's correct. Thank you. Currently, what I find a bit of a mess in LLVM and a bit difficult to deal with is the new pass manager and the old pass manager, and they're currently a bit of a mixture, and also the built-in tree and outside LLVM of a pass. Do you have any good pointers to where to find how to use the new pass manager and how to switch?
All right. So to be honest, I'm not actually familiar with the new pass manager, and I don't know. You may actually know more about it than I do. I don't know if it changes any of the requirements on passes or not. LLVM, just as for a bit of historical context, LLVM, I believe, is already on its second pass manager, and the new pass manager is the third. When we moved from the first to the second, very little changed in terms of how you registered passes or defined your passes or whatnot. I'm not sure about the new pass manager. In terms of questions, what I would do is I would ask on the LLVM developers mailing list, or if they're still using it, the IRC channel. I don't know how responsive the people developing the new pass manager will be, so I can't provide any guarantees on that. But if it were me and I had questions on it, I would, that's where I would go poke people. So I believe you had sorry, I think I answered part of your question. I think you had another question about like in tree versus out of tree, right? Oh, and I need to unmute you for that. Sorry. Yeah, I think. Yeah. Okay. So I'll give you sort of my own opinion on that, and yeah, I'll give you my own opinion. Then I'll ask whether I actually answer your question or not. But I'll give you my opinion on it. LLVM used to have this infrastructure to compile and work with LLVM extensions that were outside the LLVM source tree. And I actually worked on that build. Like I worked on the first version of that feature years and years and years ago. I don't know if that feature has been maintained, and to be quite frank, I just wouldn't use it anymore. My personal opinion is that the easiest way to do LLVM development, like if you're building something that you're not going to upstream, is you just simply make a fork of the repository, and you create a branch, and you just develop off of that branch. And then when you want to say move to a new version of LLVM, so let's say you branch at LLVM 9, or let's say 9, for example, and then LLVM 10 comes out, right? And you want to move from 9 to 10. Then what you do is you use git rebase to move your code from 9 to 10. I have found that to be a much more sane way to do things. And the reason why, it's not so much because it makes your life easier, it makes it easier for you to give your code to someone else. Because what with the old way that you do it, you'd say, okay, you have to check out this version of LLVM, then you check out my version of my code, and you have to put it here and configure it this way, and then it compiles. And of course, people make mistakes in that whole complicated process, and they're not able to compile your code. Whereas if you make a fork of LLVM, you create a branch, so you do like a git fork, and then you create your own branch, and you do your development in your own branch. Then if you want to give your code to somebody, then you just simply say, yeah, just git pull from this repository, check out this branch, and then follow the build directions for LLVM like you normally would, and everything just works. So, so in terms of dealing with that, that's how I do things now. When I was a graduate student, I've developed stuff out of tree. These days, I don't have my students do that. I have them develop everything as a branch to the original LLVM code base. Does that answer your question, or is there another pain point? There's a couple pain points for people that are working on LLVM extensions, but not trying to upstream them back to the LLVM community.
Yeah, it kind of answered my question, because I'm not an expert on LLVM, and I was trying to adopt a pass from an external source, which essentially they built it out of tree, and it was kind of a pain to do it. So I was also trying to figure out how to call it from our custom front end, and with the new and old pass manager, it was even more painful, and I still didn't figure it out. So,
I see. So like most of my LLVM usage is I'm just writing new passes. So I'm writing new machine function passes, which is part of the code generator, or LVMIR passes like we've discussed today. If you've got your own compiler and you're trying to run the new pass manager yourself, that gets a bit more difficult. I would look at what the current code is doing. So I'd look at the code, say in opt or in the code is either an opt, or if opt is just using a library to run the pass manager, it's probably somewhere in, I think, the core library in LLVM. I think it's core. It's either called core or VM core. That's where I would look for that.
okay.
Yeah. Sorry you're going through that.
No, I know. Thank you very much.
You're welcome. Other questions? Yeah, and again, like you can either ask questions on Zoom or on Slack. We're happy to answer them either way. All right. Well, Ethan, Colin, and I will stick around. People can obviously come and leave as they please. So don't feel obligated to stay if you're done with the tutorial. But Ethan, Colin, and I will stick around in case anyone has any questions. All right. Thank you, everyone. Okay, yeah, I think I'll stop recording. OC just sent me a message here. Let me. Yeah.